Syzygy, episode 66, Inscrutable Neutrons and Perplexing Pulsars. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. I'm in York. I'm talking to Emily Brunsden, who's across the other side of the country. Hi, Emily. How you doing?
Hello. Yes, I'm doing very well, thank you.
How are you getting on with the whole isolation thing? You good?
Well, I think astronomers sort of have a bit of a jump start on this because we're pretty good at isolating ourselves in remote facilities around the world. The only difference is I'm up during the daytime instead of the night. So.
Yeah. You're sort of professionally equipped for this particular. This is where you guys come to the fore, isn't it? You really should have just taken over. It's like, right, this is our time. We can rule under these circumstances. Fantastic.
Yeah, so long as there's no clouds.
Well, you're in the wrong country for that, I'm afraid. But listen, today we're talking about astronomy, not about diseases and isolation. We're talking about astronomy, and in particular, we're talking about neutron stars and pulsars. Now, if that sounds a little bit familiar, that's because you've been listening to this podcast for a while now, and you might remember that back in episode 45, which is like 20 episodes ago, we talked about the biggest possible pulsar, and maybe the biggest pulsar that could ever be that had been spotted out there in the heavens. And that was pretty exciting for astronomers at the time. Well, one of our listeners by the name of David Weingartner got in touch with us and said, hey, I've just been listening to that. I've got a couple of questions. Now, if you are a long-term listener, you'll know that we do say on every episode, hey, listen, if you want to get in touch, if you've got some questions, just send us a message and maybe we'll do an entire show about it. Well, guess what, David? This is your show. We've taken your questions about pulsars and neutron stars and we've gone, yep, we can do that. What do you reckon, Emily? Should we do that today?
They're such good questions. We thought, you know what, that we just can't do it in a few seconds. This really merits a little bit of discussion and some exciting new stuff that I learned along the way as well.
Yeah, and that's always the best one, where it's not just Emily saying, well, here's stuff that we know. It's Emily saying, did you know? I just found this out and this is awesome. So that's what we're doing today. We're drilling down into neutron stars. So before we get into David's questions, I guess, Emily, we should probably start with, what are we talking about? What's a neutron star and what's a pulsar? Should we start with neutron stars?
Yeah. So neutron stars are the kind of end products of very, very massive stars. So these are stars that live their normal part of their lives. They're normally about 8 times the mass of the sun or larger. And that means that when they die, instead of what the sun does, which kind of becomes big and puffy and fluffy, sheds all its outer layers and leaves behind this object we call a white dwarf, then there's too much mass involved in these stars and they, at the end of their lives, they explode in a supernova and they leave behind, again, a sort of compact remnant, a sort of very condensed object left behind. But in this case, it's a ball of neutrons. It's a neutron star.
It's a big lump of basically... yeah, atomic nucleus kind of soup, isn't it? It's very, very strange. Okay, so unpacking that a little bit. You've got a really big star, not really, really big, but you said sort of something like 8 times the mass of the sun. And the sun is a fairly sort of small, generic, common or garden variety bog average star, isn't it? It's not a particularly special star.
It's in the bottom third.
Yeah. So we're not talking huge, crazy big stars. We're talking bigger than the sun by sort of an order of magnitude. And when they come to the end of their lives, in other words, they run out of all of the nuclear material that they can fuse together to hold up against the gravity, then supernova. That happens. Big explosion. One of the biggest.
Big boom.
Right? Yeah.
Yep.
And loads of stuff gets thrown off into the surrounding universe. But what's left behind is this little ball of nuclear matter, neutron stuff. How does that happen? How do you get that? I mean, the explosion I kind of get, but just take us through that again. How do you get from end of life, can't hold this up anymore, supernova, neutron star?
Yeah, so the whole point of a star's life is it's always got this fine balance between the forces that are trying to condense the star, to contract it, make it smaller, and that's gravity, which depends on its mass. and then the forces that are holding up the star against this gravitational crushing, which is when the star is in its normal part of its life. This is the force that's producing from the fusion that's happening in its core. It's producing all these photons. It's pushing out with this energy from those fusion reactions and holding itself up that way. But you turn that off, you turn off fusion because it's run out of stuff to fuse, then it can no longer hold itself up against gravity, and that gravity crushes things down. And depending on how much gravity there is, then you can crush down to the size of a white dwarf, or you can go further than that and you can crush down to sort of, when I went to think about it, is you're actually crushing together all the protons and the neutrons in the nucleus. Protons and electrons in the nucleus, into the nucleus, and then you're getting this neutron sort of material left over. So proton plus electron gives you neutron.
Yeah, I mean that's slightly simplified, but actually there are nuclear reactions that say, look, if you've got a positive charge and a negative charge, we can whack those together to make a neutron. And so you've got neutrons plus all the neutrons that were already there in the atomic nuclei, and you've just got this one big nuclear soup. And the explosion, the supernova part, how does that happen? You've got all this collapse happening, but why then the extraordinary boom outwards?
So you sort of get a bit of a bounce back off this kind of object that can't crush any further. So once you get some of the layers, some of the interior layers start to fall onto this, but then they bounce back off, and then they cause an enormous pressure wave that pushes out through the rest of the layers of the X star.
Right, so you're collapsing down and it forms this incredibly dense ball in the middle, and then everything else collapsing down onto that just bounces off it because it can't, it's so dense that at this point you can't collapse it any further, and it just forms this incredibly tough, solid wall that the other stuff bounces off, and that's an extraordinarily fast and violent explosion. But what's left behind is the little ball of stuff, and it is little, isn't it? I mean, you've taken something which was really big and turned it into something which is really small and dense.
Yeah, just a few kilometers across is kind of the radius of a typical neutron star.
A few kilometers across. I mean, that's the size of, well, I mean, I'm here in York, that's just across to the other side of the city, and it's not a big city.
Yeah, York would make a great neutron star, kind of within the city walls even. Then you could turn that into a neutron star, and you'd have to cram in pretty much the mass of the sun into that sort of space.
So small and dense, and that's a neutron star, and it's weird. I mean, this is matter like nothing we ever see. It's very, very peculiar stuff. What are some of the features of neutron stars other than its insane density and very, very small size? Like what's weird about a neutron star that makes it interesting to look at?
What's not weird about a neutron star?
Where do you start?
Maybe a shorter question. But what we have to always remember is that these things aren't actually, just a lump of neutrons stuck together. These are some of the most exotic states of matter that we can imagine, let alone be able to try and measure them. So there's probably structure inside a neutron star, lots of weird extremes, if you like, of the physical kind of parameters that we've been able to measure. There's maybe some weird quantum soupy stuff going on in the core, and maybe some kind of crust, which is a little bit more understandable with our current experimental work. But neutron star research is the extreme stuff, right?
I would have guessed that in a similar way to, like, you look at a star, and a star is already fairly extreme. I mean, it's an enormous nuclear reactor with all sorts of bizarre plasma stuff happening around the outside and huge magnetic fields and stuff. It's already pretty extreme, but you get fairly hazy around the edges. Like, exactly where a star stops and starts is a little bit hazy. And I would have guessed that a neutron star would be kind of similar, that you don't just suddenly hit this uniform wall of nuclear material. You'd have weird stuff on the outside and other weird stuff going down towards the middle, and right in the middle, probably a blob of even more weird stuff. Like, it would be interesting in one of these things.
Yeah, even the textbooks have question marks in the middle of neutron stars, right?
And it's not an easy experiment to do. It's not like you can just go and visit one and go, so what are you? What's going on here? Let's get a big spade and dig some out and have a look at it. You can't do that.
No, in fact, the only way we can really go and measure neutron stars is measuring a type of neutron star called a pulsar.
Right. Okay. So this takes us on to the next part of this. What's a pulsar?
So a pulsar is a neutron star that has a beam of radiation that it's pointing out along its magnetic axis. And like a lighthouse beam, that sweeps around as the star rotates. And if we're lucky, then it will sweep through kind of the line of sight between us and the pulsar. And so we see this kind of blinking effect, if you like, a very regular pulse that's coming from the magnetic axis of the star.
It's like a cosmic lighthouse. Okay, so it's spinning. These things are spinning, and we've talked before about how when things collapse under the force of gravity, any spin, any rotational momentum that they had to begin with as a very large object, they hang on to that as they collapse down. And as you collapse down like an ice skater pulling in your arms and legs, you spin faster. And so neutron stars, pulsars, can be spinning incredibly quickly, can't they?
Yeah, the fastest one's thousands of times per second.
Like, that's even something the size of a small city. Spinning thousands of times a second that's a good effort. That's quite a lot of spin. But more than that, it's not just the spinning, it's the big magnetic fields. Now, you mentioned the magnetic fields, and that's related to these beams, these sort of lighthouse beams that come out. So magnetic fields from where? What? Why?
Yeah, well, a bit like how you've compressed down all the rotational information that the star had into a very, very condensed blob. There's some in slightly different physical ways, but you kind of condense down the magnetic field information. So these things are very, very highly magnetic, very strong magnetic fields. And those magnetic fields aren't aligned with the rotation axis. So if you imagined the lighthouse has a rotation axis which kind of goes up and down, and it's a vertical rotation axis. But the axis that the beam points out on is horizontal. It's pointing along the coast. So those two axes are not the same thing. If they were, then you'd just be pointing your beam up into the sky, and I don't know, only Batman might be able to see it.
It's not a particularly useful lighthouse. Yes, the beam from a lighthouse needs to be sort of scanning along the coast and out to sea. And that's kind of what's happening with these pulsars. You're saying that the pulsar is spinning around on its axis, and the magnetic fields are at an angle to that. And that means that you've got these magnetic fields which are rotating around the axis, a bit like a lighthouse. So what's the beam then?
So the beam has come from radio light. So what we see is a process, it's called synchrotron radiation. You've got lots of little charged particles, and they move in relation to the magnetic field. And if you've done any electromagnetism kind of 101, then charged particles in magnetic fields, you get interactions, and you're going to get, in this case, you get a bit of radio light, which is released from these mostly electrons spiraling in the magnetic field of the pulsar.
It's a bit like a version of the Earth's aurora, isn't it? Only kind of on steroids. With the aurora, you've got charged particles from the solar wind streaming out towards us, getting funneled from the Earth's magnetic field down towards the poles. And as they get concentrated down around the poles, if I've got this right, and I may not have because it's been a very long time since I've looked into it, but I think those charged particles coming down towards the poles and getting concentrated, and they kind of just, there's some energy release there, and we see that in the form of the amazing lights in the sky with the aurora. This is sort of a supercharged, highly supercharged version of that in a way, that charged particles, energetic particles, going through, interacting with the magnetic fields of the neutron star as it's spinning around incredibly quickly and just shooting out as these crazy energetic beams.
Yeah, I think that's actually a reasonable analogy. The only difference being with the aurora is that these electrons and so on, these charged particles, are then going on to interact with atoms in our atmosphere. Right. So they're interacting with nitrogen, oxygen, and that's what's causing all your colours, and that's why it's visible light.
Yeah.
Whereas these charged particles in the neutron star or pulsar are just releasing radiation just because of the spiral that they're doing, and that's in the radio.
Okay, so we have a neutron star which is spinning really, really quickly, has these big magnetic fields. It's shooting out these beams of energy off into the cosmos, and that's what we call a pulsar. One of the things about pulsars is that they do spin very, very quickly, and they spin incredibly regularly, right?
Yeah, that's right. So we can measure this radio signal. So The early pulsars that we were detecting were measuring kind of a few per second, or one blip every few seconds. The millisecond pulsars, so these are these pulsars that are really going for it, spinning thousands of times per second. There's a few examples of some of these that are still, even to this day, more precise than atomic clocks.
Wow. So how precise are we talking about? I mean, you were just saying, these are spinning at, hundreds or thousands of times a second. Like what's the level of precision?
Well, I can answer that very, very well. So
go on then.
We've got my new favourite pulsar, which is J0437/4715.
That classic, yes.
So this pulsar has a period, so this is how long it takes to do one rotation, of 0.0057574519371263 seconds.
I just kept waiting for you to stop, and you just kept going. Hang on, how many significant figures is that? That's like...
So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 significant figures. So to give you an error on that, it's 1.7 times 10 to the minus 17 is the error.
That's nuts. That's absolutely... Okay, right. So when we're talking really quite precise, that these things spin very regularly, we're not mucking around. It is hundreds or thousands of times a second to an extraordinary, unparalleled degree of accuracy. Like, what else in the universe can you think of that is that accurate, that is that precise? The only thing I can think of that might come close, and I'm not quite sure how they compare, is the experiments that have been done on the magnetic moment of electrons. That these are the tests of quantum mechanics, and those have been tested to, like, I thought it was 13 or maybe 15 significant figures. So this is on the same order. And that's nuts. This is a big ball of neutrons in the sky spinning around. That's crazy. Okay, so
yeah, that's only just some pulsars, though. I mean, most pulsars aren't as accurate as an atomic clock. I mean, they're pretty good, but they're not as good.
But even to find one, that's that's not just a lucky coincidence. That's saying something quite fundamental about a pulsar. Right? That it's possible to have one that is spinning that precisely. Okay, so we have this picture of these crazy things, which are made of crazy material that are spinning crazy fast with potentially crazy amounts of precision. Okay, so that's setting the scene for David Weingartner's questions. So he said, okay, I've just done listening to episode 45. If you haven't heard it, go back and listen to it, where we were talking about the biggest neutron star ever discovered, possibly the biggest neutron star possible. And he said, at one point, Emily, you said that astronomers think that more massive and younger pulsars spin faster. So that was something that apparently you said in that episode. Does that sound plausible? Does that sound like the sort of thing you'd say?
It sounds like something I might say.
Sounds like the sort of thing you'd say. So he says, if a younger pulsar rotates faster, does that imply that as pulsars age, their rotational speed slows down? I mean, it's a good question, right? If you can, distinguish between younger and older pulsars and say, well, the younger ones, more massive ones, spin faster, that implies that as they age, they spin slower. And yet, hang on, we've just talked about these things spinning to an incredibly, 17 significant figures degree of precision. So what is it, Emily? Are they incredibly precise spinners, or does their period of rotation change as they get older? Which one is it?
It's both of them.
Of course it is. Of course it is.
All the answers.
Yep.
So pulsars do slow down as they age. Maybe we can feel some solidarity with them about that.
Yes, I mean, who amongst us can say otherwise?
So, and maybe the clue was when I was saying that actually the most regular pulsars are these millisecond pulsars. They're the fastest pulsar sort of group that we know about. So it's actually really tricky to age a pulsar, right? To say, actually, pulsar over there, your J numbers, etc., you are 100,000 years old, or you are 70 years old, right? That's That's a really difficult measurement to make.
Yeah, I guess unless you saw it happen, unless you saw the pulsar formed, like how would you? How would you go about aging something like that?
Well, we do have a way to do it, which is called the characteristic age of a pulsar.
Okay.
And it is based on this idea that they do slow down over time. So the reason why they slow down is because you are losing energy from your system, right? This is not a closed system. When you're putting out any kind of energy, in this case it includes the radio light that's being emitted by the pulse itself. But what's also important for pulsars is that they've got this kind of magnetic braking effect, whereby the magnetic field is kind of interacting with the rotation, with all the charged particles in its vicinity. So there's a very, very slow loss of energy over time.
Right. That makes sense. You're not going to get energy out without that energy coming from somewhere. So let's just sort of agree that, sure, that makes sense.
Yeah. So what you can do is calculate its characteristic age, and it's a fairly easy calculation once you've done the measurements, which are probably a lot harder. So first of all, you've got to measure the period of the pulsar, so how long it takes to do one spin.
Mm-hmm.
And then you've got to measure the rate of change of that period.
Okay, so how quickly that period is changing. Yeah.
Yeah, so this is what we like to call in physics a p dot, which means we're looking at the rate of change of the period.
Right, so P for period, and the dot means changing over time.
Yeah, so if we take the period and divide it by twice the rate of change over time, then we get this characteristic age.
Okay.
I can give you an example. We've got a friendly pulsar that some people might be familiar with. It's called the Crab pulsar.
Right, in the Crab Nebula.
Yeah, that's right. So in 2007, we measured the period of this pulsar to be 0.0331 seconds.
Okay. I mean, that's...
No, there's a slightly larger error on that.
Yeah, I was about to say, that's fairly precise, but I mean, come on. It's not even trying.
Yeah. But we're also able to measure over, because we've been measuring this pulsar for about 50 years now. It's one of the oldest ones that we've known
One
about.
of the better known.
Yeah. So we know the rate of change of this one. It's 4.22 times 10 to the minus 13 seconds lost every second.
Right. Okay. Let's wrap our heads around that one. We're talking about a rate of change of the period, and the period is measured in seconds. So we're talking about how much change in seconds per second.
Yeah. So it's increasing by 4.22 times 10 to the minus 13 seconds every second.
Which is weird, but it does make sense. It does make sense. Okay.
It's one of these ones where the units cancel, but it's sometimes more useful to actually keep them in there just to remind us what we were talking about.
Yes, we could cancel those out, but we're choosing not to. Now, that's a very small number. It's not changing rapidly. It's, what did you say, 10 to the minus 13 seconds per second.
Per second, yeah.
Yeah.
So they're not huge changes. And they're very, very difficult to measure. I mean, you do have to really be looking at these things for decades to be able to get the precision that you need on these measurements.
Okay.
Nonetheless, we can put those numbers into our new equation for the characteristic age. Right? Yeah. And we get a number which comes out as about 1,240 years.
What's that? I mean, I'm trying to wrap my head around what that's based on, because I would have thought, like, not every pulsar forms exactly the same. You don't get pulsars formed, I would have thought, spinning at exactly the same rate as soon as they're created, because that would depend on the size of the star and so on, where they came from, right? Like the new baby neutron star is not exactly the same as every other baby neutron star, right?
They're not exactly the same, but they're, relatively close.
Okay.
There's only a small range of possible rotations and possible masses that we've been able to nail down onto these pulsars.
Right. So you're making...
So it's an approximation.
Right. You're making the approximation that to within a certain degree of happiness as an astronomer, all neutron stars are born the same, effectively. And so you're saying, well, if this one is spinning at this rate and it's changing at this rate, then it must be this old. Is that the idea?
Yeah.
Right. Okay.
So the characteristic age of the Crab pulsar was 1,240 years old. We actually know exactly when this pulsar was born. We're very, very fortunate, because the Crab Nebula is a supernova that exploded just over 1,000 years ago in 1054 AD.
Right. So we can nail that one down really well.
Yeah. So we know exactly when it was born. So that actually gives us a real age, if you like,
Yeah.
of 950 years.
And what did you say you got from the calculation? It was 1,000 and something?
1,240.
So that's not bad given the assumptions. Like if you'd said
Yeah.
it's, 100 years old or 1,000,000 years old, then you would have worried. But, you want to take it to the nearest 1,000 from the actual age and the age from the calculation, then they agree perfectly, which is pretty good.
And let's be honest, we're not really dealing with many pulsars that we know that are only about 1,000 years old. Many of them are going to be significantly older than that.
Right. Okay. Well, that's good. Okay. Well done, astronomers. So that seems to be working. So getting then onto getting back to the question, which was younger pulsars rotate faster. So they are slowing down as they age, but very, very slowly. Takes a long time.
Yeah. So what we can do is start to then, do one of the things that scientists love to do, the absolute most, is then start to put some of these data onto a diagram.
Oh, yes. I mean, everyone loves a diagram. Graph. Yep.
Nice graph.
Get some axes on there, throw some points up.
Yeah. It's a good old famous pulsar age diagram. It's called the P-dot diagram.
Well, good. Okay. So take us through it. What are our axes?
Okay. So on your x-axis, your bottom axis, what we're plotting here is how fast the pulsar is spinning. Mm-hmm. So your period from small period, which means it's spinning fast, to a very, very large period, meaning it's spinning quite slowly, right? Going left to right. And then on our y-axis going up, we have the p-dot, our rate of change. So at the bottom, then we've got the fact that it's going to be slowing down slowly. And at the top, it's going to be slowing down quickly.
Quickly, yeah. Okay.
And what we notice is that most pulsars sit kind of in the middle.
Right.
They're averagely spinning and they're averagely slowing down.
I mean, I guess that kind of makes sense. You're going to have a common or garden variety pulsar and it's going to be doing common or garden variety things. Okay, fine.
But the interesting bits are the things where, we can start to do interpretations. It's the bits that aren't the ordinary, the average bits.
Sure. So what happens when you get away from the norm?
Okay, so we look at, first of all, where pulsars are born. So where you've just had your supernova, you've got your brand new baby pulsar, where is it going to sit in this diagram?
Okay, now if
Take a stab.
So they're going to be spinning the fastest, right? So they're going to have the smallest, shortest period. So they're going to be over on the left side of this diagram.
Yep.
And they are, I'm guessing, going to be also their rate of change is going to be fastest because the speed of their rotation means that their magnetic fields are doing all sorts of crazy things and they're spewing out energy all over the place, and that's going to mean that they're losing energy the fastest, so they're going to be changing the fastest. So they're going to be top left.
Fantastic.
Hey,
well
I could be an astronomer.
Yeah,
that'd be awesome.
Good bit of reasoning too. Yeah. I like it. Yeah. So pulsars are born in the top left part of our graph, and then they sort of move in a diagonal-ish way down towards the bottom right as they get older.
Right, because their period gets longer. And as their period gets longer, I guess that also means that their rate of losing energy is going down, which means their rate of change is going down. So they're traveling diagonally down.
Yeah.
They get slower and slower, but they also get slower and slower, slower and slower. How's that for a summary?
If you go all the way down to the slow part of the diagram and to the bottom right, this is actually a special region of the diagram which is called the pulsar graveyard.
Where pulsars go to die. Oh dear. What's your sort of slowest? What's your slowest pulsar? Like, how slow do we see them?
Well, those are two very, very interesting questions because one of them we know the answer to and one of them we don't.
Oh, okay. So, I guess my question I thought was a rephrasing of the same question, which was what's the slowest we've seen? But I guess you could also interpret it as how slow can they be?
Yeah. So the slowest we've seen, and that we know of, is around about 8 seconds. Mm-hmm. Because if you get any slower than 8 seconds, then actually all the physics, the conditions needed to create this pulse, the radio emission, no longer exist. They cease.
Oh,
right?
Okay. So you could conceivably have a pulsar spinning slower than that you can't see, which I guess makes it not a pulsar anymore. It's just a neutron star at that point.
Yeah, but it's still spinning and it's
Sure.
still alive.
Sure.
I guess.
And it'd be spitting
for as
out.
much of alive as you can be as a pulsar.
So would it be spitting out some energy, or are you saying that all of that physics just fell over and it doesn't have any beams at all?
You don't have a strong enough magnetic field to really create synchrotron radiation.
Okay, so it's just a spinning neutron star, just a spinning neutron star.
Yeah,
Cool.
yeah.
But
So,
8 seconds,
so we can't see them.
we've seen them. We've seen them that slow,
8 seconds is the limit. I don't think we've got any that are quite that slow.
right?
We definitely have some that are on the whole seconds kind of scale. I'm not sure what the slowest one is, but it's around about there.
Cool. All right. So on our diagram, we started with the baby neutron stars up in the top left, and then we travel our way down to the bottom right, which is the pulsar graveyard. So is that it? Is that it for our diagram?
Well, it kind of would be, except there's a group of pulsars that don't follow this trend at all.
Of course, because the universe is weird, and as if this wasn't weird enough. Okay, so who are these pulsars? What are they? What's their story?
So there are some pulsars that are spinning very fast, but they're also slowing down very slowly.
They're spinning. So they're over on the left, but they're down the bottom.
Yeah.
Bottom left.
They're away,
Not top
separated
left,
from
bottom.
everybody else.
What's
Yeah.
going on there? Who are they?
Well, these are really interesting pulsars. These are pulsars in binary systems.
Okay, so they have a star companion?
Well, usually another pulsar,
Okay,
or
two
or at
pulsars.
least another neutron star.
Right. So why
Usually
would
it's
that
another compact object. Yeah.
change how quickly or not quickly they're slowing down?
So the thing is, now you've not only got the rotation of the pulsar, but you've got an orbital motion as well.
Right.
And there's interactions between objects that spin and objects that orbit. Our moon is the great example, whereby the moon is orbiting the Earth, but it's also rotating. And over time, those two, if you like, rotations have interacted, and now the moon is rotating at exactly the same rate as it's orbiting the Earth.
Gets into lockstep. It's what's it called? Tidal locking? Is that
Tidal
right?
locking.
Yeah. And Mercury does the same, doesn't it? In its
Yeah,
orbit around
Mercury's
the
on its
sun.
way to being tidally locked to the sun.
Yeah. So with these two neutron stars in a binary system, something similar. They get tidally locked.
Yeah, well, all objects eventually will. If they're spinning and orbiting, then eventually tidal locking is what's going to happen if you wait long enough in the universe. But I think probably just the easiest way to think about it is that there's now this extra component, this extra orbit that's messing about with the rotation of the pulsar, and so it does something a little bit different.
Right. So
It doesn't slow down as fast.
could that mean that it's harder, in a sense, for the neutron stars to slow down because of this tidal locking? That because their rotational motions in these different ways are kind of chained together, it kind of the physics of that sort of says, well, not so fast. You could lose some energy by spitting out these beams, but it's going to be pretty hard for us all to start slowing down the way you want to. So we're just not going to. We're just going to keep spinning at this speed. Is that kind of how it works?
Yeah. So you've got interaction between the two. So you've got an energy source in some ways for some of these pulsars from the orbital energy.
Right. That's very cool. It's very cool. I hadn't thought about that before, but that's a really nice idea. Okay. So that's the weird part of our diagram. Are there any other weird parts of this diagram that we know? Like, is there anything up in the, hang on, we've got top left, bottom right. Is there anything top right?
Well, look, I'm going to show you my diagram right now and see.
Oh, yeah. Okay.
It's not a very accurate scientific diagram.
That's, I mean,
It's
there's
more
a
like
lot of
stuff happens here.
there's a lot of room for maneuver there, really, isn't there? I think you should take a picture of that. We'll put that up in the show notes. Emily's diagram of pulsars. Okay, that gives us a lot to chew on about the pulsars and the way that they age, the way they go from being newborn, spinning quickly, but aging quickly out to the graveyard, where they're just gradually slowing down, unless they're in a binary system, in which case they're doing something else entirely. Which then kind of takes us on to the second part of David Weingartner's questions, which was, he said, I've also wondered at the lower limit of the size of neutron stars. I found some discussion online that, he says, modestly, I can barely understand. Look, frankly, David, I think if you can understand it all, you're doing well. But saw the value of 1.4 solar masses as being what the lower limit of the size of neutron stars, close to 1.5 times the mass of our sun. So first of all, Emily, is that right? 1.4 solar masses is the lower limit?
Well, it kind of depends on how you want to think about this. So I looked into this from a few different perspectives, and
it's never simple, is it? It's never simple.
No, it's never simple, but it's interesting. And okay, let's start from one perspective. Mm-hmm. One perspective could be, you could ask, well, to determine the lower limit of a neutron star, if you just took neutrons and made them into a ball, what's the smallest ball you could create with your neutrons, right?
Okay.
And that minimum turns out to be about 0.1 solar masses, so a tenth the size of the sun.
Okay, so that's the smallest that you could just naively compact stuff together and have it sitting there as a blob. Is that what you're saying?
Yeah. So if you just gathered neutrons, threw them together until they're stuck into a blob, then that's your smallest blob.
So what happens if you try to go smaller than that? That it just can't hold itself together gravitationally?
That's right.
That it will fly apart?
It doesn't have enough nuclear forces to hold into a sphere.
Right.
So
okay.
It just sort of falls apart.
All right. So a tenth of a solar mass, but I'm guessing it's not that simple.
Yeah, no, not quite, because that's definitely not how neutron stars are formed.
No.
So
it's much more violent than that.
It is. So if we're going to look at real neutron stars are formed from the collapse of material, right? And we sort of alluded to a little bit how you crunch down stuff for a low mass star and you get a white dwarf.
Yeah.
Now, there's an upper limit on a white dwarf. A white dwarf star is the core of an old star being crushed together, and it's held up by electron degeneracy pressure, right? So it's still got protons and neutrons floating around in this very dense ball, but the electrons don't like being near each other. They can't be in the same quantum state.
Yeah,
right?
it's a weird quirk of quantum mechanics, isn't it? That certain types of particles, like electrons, like protons, don't like being in the same state. They don't like being exactly the same. They have to be in different places, different orbits, different atoms. They have to be different. And the more you squeeze them down together, the more they say, no, we're not going to do this. And that itself forms a kind of pressure that helps to push against the gravity. It's that degeneracy pressure. So
stepping down through the physics, if you like, you can think about the pressure or the force. If you try to stick two negative charges together, right, that's Coulomb force, pushing those two apart. You overcome Coulomb force, then you've got, and you still got this material, then you can have the electron degeneracy pressure, or this force which is holding up everything inside the star. Now, there's a mass limit to your white dwarf star, whereby if you exceed that, then the gravity is too large. It's going to overcome this electron degeneracy pressure, right?
And what happens at that point when you overcome that? Because the rules of quantum mechanics are quite firm. It says, no, you won't do this.
It does say
so
no.
What kicks in at that point that says, all right, we found a loophole? How do you get past electron degeneracy rules?
So you can't stick the electrons any closer together. So you just get rid of the electrons. That's the simple way.
So that's the electrons going, hey, proton, over here, you and me form a neutron, we'll get past this. And you get get neutrons, which is where you get a neutron star. But that only happens when you're above a certain mass. You got to have a lot of gravitational pull to get over that.
And that mass is 1.44 solar masses.
Okay, so that's where the 1.4.
The Chandrasekhar limit.
Right, that's where that comes from. Is if you have that amount of mass, you've got enough gravity to say, come on, let's turn on that particular nuclear reaction. Let's get rid of the electrons. Let's make a whole bunch of neutrons and make some new kind of weird quantum sludge called a neutron star. Yeah,
and that would be a good way to say, well, that's therefore the size of a neutron star, the minimum size. Because if it's more than 1.4 solar masses, then you're going to get a neutron star that's bigger than that. And if it's less than that, no neutron star.
Just get a white dwarf. Sure. Okay. Seems reasonable. You're about to tell me that it's not that simple either.
It's not quite that simple, right. Unfortunately. So, the problem is that you're not just talking about a ball of electrons and protons and neutrons that's just sitting out there in the vacuum of space not doing anything.
Right.
Other bits of physics are involved. Rotation is a really important one. So actually rotation changes the physics of what you're doing, because rotation can change max and minimum sizes and limits and things. You've also got electromagnetic forces in here. But what's, I guess, the most critical way you could describe your neutron star, the thing that everything depends upon for a neutron star, is something called an equation of state.
Mm-hmm.
And an equation of state is something that describes the internal workings of your neutron star, how your pressure is related to the density inside your star.
Okay, so it's trying to strip the description of a neutron star down to, all right, what's a few basic parameters that we can talk about? And it's what? Pressure, density, temperature, these sorts of things?
So equations of state are mostly to do with pressure and density. And, well, actually, so people have done some elementary physics, either like A-level physics or some early university physics, might already know of one very famous equation of state, which is called the ideal gas law.
Yeah, which is where I was kind of going with that. That's your sort of PV equals nRT, if you remember that from your high school days, and it's relating for a fluid or for a gas, an ideal gas, hence the name. What P is pressure, V volume, N is the number, the density basically, isn't it? And R is a number, and T is the temperature. So it's relating pressure, volume, amount of gas, and temperature in a very elegant and quite simple way, and that's an ideal gas. So that's an example of what we would mean by equation of state, and you're saying that neutron stars have their own version of that.
Yeah. So in fact, it's a huge area of research that is going into how do you actually construct an equation of state of a neutron star? How do you test an equation of state of a neutron star? Very interesting. So I guess to be able to do that, then we need some data on real neutron stars, right? We need to know, okay, we've got some theoretical models, we've got some equations of state that we want to figure out which one is most accurate. We need some hard data to kind of look at that.
Sure.
And the first piece of data you need is, of course, the mass of your neutron star. That's going to tell you a lot about the physics that you've got going on. Turns out that that's a really hard thing to try and measure again.
Okay, and why is that so hard? I mean, I'm not going to deny it probably sounds quite hard, but why is that so hard? We can measure the mass of other things. Why is it so hard with neutron stars?
Well, it's actually very similar to the problem of measuring the mass of any object in the universe. You've got a star that's sort of floating out there in the galaxy. How do you measure its mass? You can't, tip it on some scales. You need some gravity to make it sit on some scales. Most of the ways that we measure mass for, say, a star are actually based on models of saying, well, the stars are, this temperature is probably about this density, therefore we can kind of figure out roughly what the mass is. And, if we're off by, the mass of the sun-ish, that's maybe, a good measurement.
Yeah, that's not too bad. So what you're saying is that while we're used to the notion of, well, we can just measure the mass of things here on Earth, actually, in astronomy, you've got to build up a chain of reasoning, which is, well, we know this thing, and we know that these things are like those things, and they have influence on these other things. And so through all of that, we can infer the mass of this star or of this galaxy or of this whatever it is. And with neutron stars, you need its own set of reasoning to be able to get to the mass. And that's not simple.
Yeah. And it's actually the same sort of reasoning and the same, we can do some direct measurements, just like we can do some direct measurements with stars. And those are stars or indeed neutron stars in binary systems.
Okay. Yes, I remember you saying in the past that binary systems gives us a whole bunch of information that we wouldn't normally be able to get.
Yeah, because you can understand the orbital properties, which are things you can observe. Then it's just solving the Kepler's laws or Newtonian mechanics to get the individual masses of the two things in your system.
Right, I see.
So we can do this for binaries. We don't have a lot of neutron stars and binaries. The latest sort of plot I saw maybe on the order of 20, if we're lucky.
Well, that's enough to start with, at least. That gives you some information.
Yeah. So if you take these 20 or so stars, then we get an average mass of about 1.35 solar masses.
Isn't that a bit lower than the 1.44?
It's a bit lower, but you get, again, equation of state, that's
allowed. Okay, close enough. All right. Round it to the nearest 1.4.
The typical errors on these measurements are about half a solar mass.
Okay, so 1.35 plus or minus a half. That's
Yeah.
in agreement. That's in experimental agreement with the theoretical.
So it all sounds a bit bleak at this point, but I think what's interesting, and I did look into a little bit more on these equations of state, is that it does start to at least narrow down some of these equations. So we have different categories of equations of state. We call soft ones, which are where I guess they're just more flexible. They're a bit spongier.
Yeah, they're happy to bend with the wind of of experimental evidence. Perhaps they're easily they're malleable.
It is kind of a so these are less, I guess, rigid stars you could think about. So they have a maximum mass of something like 1.5 solar masses.
Mm-hmm.
And if you talk about a hard equation of state, then you can actually make that a little bit bigger. So with a hard equation of state or a kind of firmer, more rigid star, then you're getting up to 2.5 times the mass of the sun as your maximum.
Okay.
We do have some other sort of things to feed in. We do know that if you go larger than about 3.2 times the mass of the sun, then you've broken general relativity. So you're not allowed to do that.
Okay, right. Because we don't want to do that. That would upset Einstein and probably all sorts of physical principles as well. So let's not do that. So over 3 and a bit, don't go there. But as long as we're under 3 and a bit and more than about 1.4, we're well and truly within neutron star range. So that's all good.
Yeah. So I think it is quite good. We've got a range, and we are trying to use more and more measurements of these neutron stars to try and figure it out. But it's probably actually a fairly narrow range in the region of 1.35 solar masses for all neutron stars.
So that does then kind of answer David's question, doesn't it? He was asking, we've got the value of around about 1.4, 1.35 solar masses. He then went on to say, what's the physical size of these lower limit stars? I mean, I'm assuming he's talking sort of physical dimensions. We're talking a couple of Ks across then.
Yeah. We don't have really good measurements on this at all, which is why we tend to prefer mass, because mass is something we can directly measure from these binary systems.
Right.
And then you could pick an equation of state, and that will give you the radius, but
you don't know whether that's right. So it's going to be small, very dense, very compact. Sure, let's say a couple of miles across. And in the order of 1.35, 1.4 solar masses. Okay. So the last thing that David asked was, are there small, non-energy spewing, invisible neutron stars traveling around the universe? And I guess this harks back to what you said before, which is, look, as you slow down a neutron star, you get to the point where the beams turn off, that the processes that create these energetic beams that fly off across the universe and form these lighthouse type beams that we can see. Those processes can't work anymore once you start going slower than about 8 seconds or so as your period. So does that mean that the universe could just have a whole bunch of invisible neutron stars that we don't see?
It could do. I think this is where we've been really naughty, I think, as astronomers over the last few decades, whereby we have two definitions for what are broadly, at the moment, the same thing, but we don't actually know if they always are the same thing.
Sorry, is this neutron stars and pulsars, or?
That's neutron stars and pulsars. Right. So we observe pulsars, right? We see the radio signal. That's how we know that the object is there. That's our measurement, if you like. We can measure, even when we're measuring these pulsars and binaries, we are measuring the binary orbit via that light. And we're not seeing these stars. They don't shed any optical light, so we don't...
So are you saying that the only neutron stars that we've ever observed are pulsars? All pulsars are neutron stars, but can you turn that around and say all neutron stars are pulsars?
Well, this is the big question. So all the ones we've observed, at least in the radio, via these lighthouse effects, are pulsars.
By definition, I mean, that's a tautological statement, isn't it? This is where the naughtiness comes in.
We do have some measurements of neutron stars that are not from this signature, we have had neutron star mergers, which we have detected via the gravitational waves.
This is LIGO and that crazy stuff over the last half a decade of measuring these ludicrously small effects of gravitational waves coming across the universe from when neutron stars collide. And that's one of the most energetic things ever, isn't it? That's a crazy amount of energy given off, which we detect as one minute fraction of the size of an atomic width's wobble in space-time. I mean, it really is absolutely nuts. That's what you're talking about, these neutron star mergers.
That's what I'm talking about.
I hadn't thought about that. So you can see neutron stars through gravitational waves. What you don't know is, were those neutron stars pulsars? Because you didn't see them that way.
We don't know. They're far too distant for us to have detected, even if we had known that they were there beforehand, which we didn't.
But you would have known their masses, at least to some degree, from the gravitational wave measurements. Isn't that a thing?
Yeah, but their masses are kind of, in the range of this 1.35,
right,
etc. solar masses, right? It doesn't tell us, were they in the pulsar graveyard, shall we say, of being rotating slower than, or having periods longer than 8 seconds.
The whole point of that plot is measuring the period, which you get from seeing the things spinning around, which you're clearly not doing in this case. So you've got this gap, haven't you? Which is, on the one hand, everything that we've measured does this, but now we've got this other way of measuring things with gravitational waves, which is utterly disconnected from the other way that we used to look at these things. And at this point, no way to bridge that gap, because
not at this time, unfortunately.
Unless a pair of neutron stars that you have been observing decides to fairly rapidly come in on itself and merge, which you can watch, like that'd be cool, but you've only seen 20 of them. The chances of that is pretty slim. You'd have to be very lucky.
Yeah. So I think if we just approached it from a logical point of view, it would seem like it would be a natural kind of thing that neutron stars are born as pulsars, and then maybe if they live long enough, then they slow down and then enter this pulsar graveyard and then just sort of hang out there for the rest of eternity, kind of like just dead remnants of stuff. But we have absolutely no evidence for that.
But I mean, that's kind of cool. I hadn't actually appreciated that in all the reading that I'd done about the gravitational wave stuff. I hadn't put it together that it's this new way of doing neutron star stuff that is so different. I mean, that's very cool and very exciting, but it does kind of bring out, as you say, the naughtiness of the astronomers, which is, when we talk about neutron stars, we're really talking about this thing. And maybe there's a whole side to them that we don't know about because we don't measure them that way.
Yeah, and I think it's fair to say that quite a lot of models of neutron stars kind of ignore the fact that they might be pulsars. It's kind of easy to ignore the magnetic, well, it's not easy, it makes the maths easier sometimes if you ignore the magnetic field effect.
Magnetic fields just mess everything up, really. In terms of the maths, it just makes it so much harder. And yet that's a fairly significant component of the whole pulsar thing, is the magnetic field. So maybe ignoring those.
But to be fair, you can use this data now so we've got data from the masses of the pulsars that we've been measuring to work out what the equation of state actually is. We've now got a whole set of new data that's completely disassociated with that should be telling us the same answer, but from a different set of physics. So those two hopefully will start to converge very soon.
Well, David Weingartner, I really hope that this episode has answered your questions. I think we've certainly given it a red hot go anyway, Emily. I think we've done neutron stars and pulsars in about as much detail as we're going to be able to for a while. I'm not saying we'll never talk about them ever again, but I think we've done a pretty good job.
Oh, I love them. They're really, really good. I'm so excited to learn about the P-dot diagram.
Oh, yes. I mean, that's made my day. I'm going to go and talk to my family about that over here in isolation and really, really make their week. Listen, we are going to have to find our way out of this one. If you want to get in touch with us, like David did, you've got a burning question coming out of one of the episodes that you've just listened to, or some other question about your wonderings and ponderings about the universe, you can get in touch with us. There's all sorts of different ways that you can get in touch with us. Emily, name some.
We are socially isolating on the internet.
We are Social Isolation Media.
So we are at SyzygyPod on Twitter. So SYZYGY Pod on Twitter. On the Facebook, on the Instagram, on, syzygy.fm, the website.
That's right. I mean, I think, we'll call it quits on the social media there for a while. We're not going to do TikTok or anything like that. That's just silly. But yes, syzygy.fm. There you can find all of our past episodes, all of the show notes. You can find a contact form, which is what David did. Get in touch with us and send us some questions, or you can just, send us a message through Twitter or through Facebook or whichever format you prefer. The bottom line is get in touch, say hi, tell us what's on your mind. If you want to help out the show, a couple of different ways that you can do that. You can, the biggest thing is talk it up, spread the word, tell people that you reckon might have an interest in the world of astronomy, astrophysics, the universe, the cosmos, and tell them you found this amazing show called Syzygy. Spread it around. It helps us to rise up through the noise. The other thing you can do is leave us a review and a bunch of stars on your podcast client of choice. And one last way that you can help us, if you're interested in helping us to keep the lights on and the electrons flowing through the Syzygy podcast universe, is to go over to Patreon and become a patron of the show. Patreon.com/SyzygyPod and sign up to become a financial supporter of the show, and we will be forever in your gratitude. It helps us to keep the website going. It helps us to keep the syzygy.fm domain name, and it helps us to plan new things for the future. We do live events. We like to go to podcast festivals when they're running, when you can go outside and do stuff. We'll be wanting to do that in the future. So if you want to do that, we would love you forever. That would be fantastic. But otherwise, I think it's time to finish this one up. So we'll be back again in about a week or two. Until then, Emily, I'll catch you later.
See you later.
Bye, everybody.
I'm just looking for my notes on 45.
Notes on 45, which is different from stars on 45, which is
Here it is. Episode 45 is written on loose paper instead of in my notebook on the back of my notes that I made for my Are You Allowed to Live Here Forever test.
there you are.
So it also has pieces of information on it that are quite useful. For example, the fact the population of the UK in 1600 was 4 million people.
Important to know when you're going to become a permanent resident and potentially a citizen is how many people have lived in the country 400 and something years ago. Yeah, really important.